Okay, let's unpack this. For years, hydrogen has been whispered about as the missing link in the global clean energy transition.
It really has. It's this idea of the ultimate energy carrier.
Right. The thing that promises to solve that thorny problem of bridging intermittent renewables like solar and wind with the constant heavy-duty demands of logistics and industry.
But, turning that promise into market reality isn't just one single leap.
No, it's a marathon of manufacturing and materials science breakthroughs.
Precisely. And for you, our listener, who wants to move beyond the high-level headlines, our mission today is to conduct a really professional, in-depth analysis of the fuel cell technology RoadMap 3.0 or RootMap 3.0.
And you should think of this document less as a wish list and more as a detailed strategic blueprint.
Exactly. It's designed to tackle the challenges of scaling an entirely new industrial ecosystem all the way up to 2040. We are going to be dissecting the current status, the very aggressive vision for the next 2 decades, and the incredibly detailed milestones.
And those milestones are across 4 critical layers of technology, right?
That's right. The vehicle, the system, the stack, and then the fundamental material science that's underneath it all.
The strategic gravity of this document, I mean, it really can't be overstated.
No, it can't.
We're discussing a technology that is now underpinned by a formal legal mandate, thanks to the inclusion of hydrogen in the energy management scope, with the energy law that passed back in November 2024.
And that changes everything. It shifts this from optional R&D to a national strategic imperative.
And when you place that alongside the global push, like the EU making hydrogen a core priority, or Japan setting that enormous 2050 target of 20 million tons, you see why every single detail in this roadmap matters.
What's fascinating from a strategic perspective is the document's explicit identification of fuel cell vehicles, FCVs, as the absolute focal point.
The pioneering field, as they call it.
The pioneering field, yes. It has to succeed first. The thinking is clear. If FCVs, especially the heavy-duty ones, can achieve commercial viability, they create the mass demand needed to pull the entire upstream green hydrogen industry.
Production, storage, logistics, all of it.
All of it. Into existence. The entire architecture of this roadmap is built on forcing breakthroughs in the vehicles that will then cascade down and solve the challenges at the materials level.
So if the FCV is the linchpin, where exactly does the industry stand today? Before we look at the 2040 vision, we have to look at the diagnosis of the current state, which the previous plan, RoadMap 2.0, laid bare.
Right.
And that diagnosis is summed up in a very professional phrase: application lead, core lag.
That phrase, application lead core lag, provides the foundational analysis for the entire 3.0 strategy. It means the industry has excelled in system integration, in scaling up vehicle deployment, and demonstrating real engineering prowess in the field. That's the application lead.
And they moved fast. The assessment of RoadMap 2.0 found that about 75% of the key technical indicators set for 2025 were either met or on track by 2023.
That execution speed is phenomenal. It really is.
But the core lag implies that success is, well, brittle. Where are those other 25% of indicators, specifically the 14% identified as definitively lagging, that are undermining the long-term viability?
They are concentrated entirely in the core metrics: cost and durability.
Of course.
It's specifically passenger vehicle life and cost, and for commercial vehicles, cost and system life. This is the structural weakness. You can build a fantastic 270 kilowatt fuel cell bus, but if the stack life is too short, the total cost of ownership, the TCO, it just becomes prohibitive.
Right, compared to diesel or even the newer battery electric alternatives.
Exactly. That lag dictates the entire strategy moving forward.
So let's focus on the application lead side first, because the progress in commercial vehicles, or CVs, is undeniable. They lead globally in sheer volume and real-world field validation.
The momentum is staggering. I mean, consider the fuel cell system power for CVs. It soared from an average of just 30 kilowatts in 2020.
30 kilowatts? That's barely anything for a commercial vehicle.
I know. It soared to an industry high of 270 kilowatts at 2023. That's a 9-fold increase in power in just 3 years. Wow. And vehicle life saw a massive reliability jump, going from only 100,000 kilometers to approximately 400,000.
Okay, so that's 4 times the operational life. That starts to get appealing for fleet operators.
It does. But for those operators, power and life are important, but cost is king.
So what happened to the economics?
They improved dramatically. A benchmark 12-meter fuel cell bus cost roughly 3 million CNY in 2020. By 2023, that had dropped to between 1 and 1.5 million CNY.
So a 50 to 66% cost reduction in 3 years. That's not incremental.
Not at all. This is a paradigm shift in manufacturing scale and supply chain rationalization.
Yeah.
And on top of that, efficiency improved. Hydrogen consumption for that same bus dropped from 7 kilograms per 100 kilometers to a much more manageable 5.
That rapid improvement explains the deployment success. Now, shifting to passenger vehicles, PVs, are they showing the same kind of exponential gains?
They're following the commercial lead, but as we noted, they still slightly trail the international top tier.
In what areas specifically?
Market-ready features and durability. They did achieve a major win in cold start capability, improving from minus 20 degrees Celsius down to minus 30.
Which is a key necessity for northern climates.
Absolutely. And they demonstrated competitive fuel economy. Some models are getting as low as 0.65 kilograms per 100 kilometers.
But when you look at the international benchmarks, say the Toyota Mirai, where does the domestic offering fall short, beyond just the cost?
The primary performance lags are range and durability. International models are getting between 600 and 800 kilometers of range, while domestic is more like 500 to 700.
So it's narrowing, but it's still a gap.
Right. But the durability gap is far more critical for consumer trust and, warranty liability. The analysis is very clear that domestic EVs are lagging significantly in achieving the lifetime targets necessary for widespread acceptance.
Okay, let's zoom in on the fuel cell system assessment. The RoadMap notes that commercial vehicle systems moved from catching up in 2020 to parallel running with global leaders by 2023. How should we interpret parallel running when they also report a core lag?
It's a great question. Parallel running means they are competitive in many of the peak performance metrics. They are, in fact, leading in raw power output.
Leading?
Yes. The domestic maximum CV system power hit 270 kilowatts compared to an observed international maximum of 190 kilowatts. They're also highly competitive on initial cost, around 2,000 CNY per kilowatt, and efficiency at around 64%.
So if they lead on power and they match on efficiency and initial cost, the Achilles heel has to be the system life. This is where that core lag really shows up.
Absolutely. This is the single most persistent failure point identified in the RoadMap 2.0 evaluation. The highest system life achieved domestically is 20,000 hours. The international target, and in some cases the benchmark, is over 30,000 hours.
A 10,000-hour gap. For a fleet operator buying a heavy-duty truck, what is that difference, 20,000 hours versus 30,000? What does that actually translate to in terms of total cost of ownership risk?
The impact is massive. A heavy truck operating around the clock can easily hit 4,000, maybe 5,000 hours per year.
Okay.
A 20,000-hour life means a mandated expensive system replacement in year 4 or 5. A 30,000-hour life pushes that out to year 6 or 7, potentially covering the entire depreciation schedule of the vehicle.
So that 10,000-hour difference directly reduces the TCO. Less downtime, less maintenance, lower amortized cost.
Precisely. Without closing this durability gap, the whole FCV value proposition for logistics just falls apart financially. The RoadMap knows this, which is why that durability metric is the core challenge.
And before you move deeper into the stack, what about the balance of plant? The supporting systems like compressors and pumps, are they a problem area?
No, actually. The BOP components are largely moving out of the core lag category. They're achieving localization and parity quite rapidly.
So, for example, the air compressor.
It's now near international advanced levels. It's achieving over 95% efficiency, especially with an expander for energy recovery. The remaining gaps are minor things like maximum speed and noise control. Those are optimization issues, not fundamental barriers.
And the hydrogen circulation systems?
Mostly localized and showing strong durability figures. The report highlights performance decay of less than 2% after 300,000 cycles. So the application layer and the peripheral systems are largely robust.
So the problem isn't the supporting cast.
No, it's the protagonist, the fuel cell stack, and the materials that make it up.
Which brings us to the most complex part of this analysis, moving inside the system to the stack itself. This is where the core lag is truly rooted. Let's talk about the fuel cell stacks.
The stack performance data from 2019 to 2023 shows incredible engineering optimization. I mean, domestic power density and raw stack power are highly competitive globally.
We're talking world-class on those power metrics.
We are. Some manufacturers have reported peak power over 400 kilowatts, with power densities reaching an impressive 6.45 kilowatts per liter.
But the reality check is always cost and lifespan. We already know the system life is lagging. How does that translate down to the stack level?
The lag is even more pronounced here. The international benchmark for a commercial vehicle stack lifespan is over 25,000 hours. The domestic highest predicted value is only 16,500 hours.
So there's the source of that TCO problem right there.
That's it. And cost is the other half of the equation. The domestic average CV stack cost is 1,000 CNY per kilowatt, which is still significantly behind the international average of about 800. So the strategy has to be this two-pronged attack: get the cost below 800 and push the life beyond 25,000 hours.
Let's focus on the structural components, the bipolar plates or BPs. These are complex and they demand extremely precise, high-volume manufacturing. You mentioned two types.
Correct. Metal BPs, which are essential for high power density because they're thin and conductive, but their corrosion-resistant coating is complex and costly.
And the other type.
Carbon-based plates, like graphite composites. They offer better inherent chemical stability, but they often sacrifice power density because they're thicker.
The source highlighted a big technical achievement in metal BPs, achieving a microflow channel aspect ratio of greater than or equal to 0.7.
Yes, matching top-tier competitors like the Toyota MIII Gen 2, this suggests engineering design parity has been reached.
Which is a huge victory.
It is. Improving that aspect ratio is crucial for gas distribution and heat removal. And what's more, domestic material companies like Taigang and Bayo Steels have successfully developed the specialized stainless steel and iron alloys for the base metal, breaking a long-standing international monopoly.
So the materials foundation and the design are largely solved. Where then is the cost bottleneck within the bipolar plate layer?
It's in the manufacturing efficiency and the post-processing specifically, that coating process for the metal plates.
How big is that gap?
The U.S. Department of Energy, the DOE, set a benchmark target of $2 per kilowatt for bipolar plates by 2025. The current domestic cost is reported at $5.04 per kilowatt.
So more than double. That's a massive commercial burden. What makes that coating process so expensive?
Well, the coating itself, which provides the corrosion resistance, can account for up to 60% of the cost of the metal plate. Domestic production lags here. The technical hurdles are in achieving ultra-low corrosion current density.
And that difference, even if it seems tiny, dictates the chemical stability and the lifespan.
Exactly. When you're stamping and coating millions of plates, every fraction of a microamp of corrosion current translates into reduced stack life and higher replacement costs. The manufacturing efficiency just isn't fast or precise enough yet to hit that $2 per kilowatt benchmark.
Okay, let's drill down even further to the membrane electrode assembly, the MEA. This is the ultimate core, the actual chemical reactor.
The MEA is the chemical heart, and the story here is surprisingly mixed. By 2024, MEA performance has largely caught up. Power density hit 1.6 watts per square centimeter, and the lifespan hit 20,000 hours, which is aligned with advanced international levels.
That's a substantial achievement.
It is. But the big surprise you noted earlier was the platinum loading advantage.
Right. Tell me more of that.
Yes, this is a critical commercial win. Domestic MEA has achieved a lower platinum, or PAD, loading 0.25 milligrams per square centimeter compared to the 0.3 that's typical in international products.
And since platinum is the single most expensive material in the entire system?
It gives domestic developers an inherent structural cost advantage moving forward, as long as they can scale production.
That seems like a massive lead. Why then does the source material state that the critical materials layer is the weakest link, the comprehensive lag, and still restricts the overall stack performance?
Because while the overall design might be competitive and the PT density in the MEA is lower, the consistency and fundamental science of the three key materials, the PEM, the catalyst, and the GDL, are holding the entire system hostage. This is where reliability breaks down.
Let's start with the proton exchange membrane, the PEM. What's the fundamental lag there?
It's all about manufacturing precision and consistency. Production capacity is increasing rapidly, but the key technical barrier is thickness consistency. Domestic PMs are achieving a thickness consistency of plus or minus 1 micron. The international advanced level is plus or minus 0.75 microns.
Why is a quarter of a micron difference so critical for durability?
Well, the membrane manages water, heat, and proton transport. Any microscopic thickness variation creates hotspots, uneven hydration, localized stresses.
Which dramatically accelerate degradation.
Exactly. This lack of uniformity at scale is a direct threat to achieving that 40,000-hour system life target. It makes the entire stack vulnerable to premature failure.
And what about the catalysts? Despite the lower MEA PT loading, there's still a cost problem.
The cost problem stems from the PT per kilowatt. The domestic average for the system is still 0.3 grams per kilowatt. You contrast that with commercial leaders like Toyota, who have achieved 0.17 grams per kilowatt in their applications.
And the long-term goal is even lower.
Much lower, sub zero point 0.1 grams per kilowatt. Until the industry can have the PTUs per unit of power, the economics remain vulnerable to the price and scarcity of platinum.
Finally, the often overlooked component, the gas diffusion layer, or GDL. The roadmap says there's a heavy reliance on foreign suppliers. What's the technical issue?
The GDL manages the mass transport of gases and water. Domestic products suffer from poor batch consistency and a narrow operating temperature range.
And that inconsistency comes from where?
It's traced back to the fiber dispersion technology used during production. If the porosity is uneven across the sheet, the stack's performance fluctuates wildly, especially at high power. It limits the heat and mass transfer capacity, which restricts reliability and reinforces that entire comprehensive lag status.
So if we synthesize this current status, the industry has built competitive, high-power systems and vehicles, great application scale.
Right.
But that scale sits on a fragile foundation defined by a reliability deficit, traced directly back to manufacturing precision and material consistency in PEM thickness, GDL uniformity, and the high PT content. The mission of RoadMap 3.0, then, has to be to fortify that foundation.
That is the perfect summary. The entire strategy up to 2040 is a phased attack on the durability and cost metrics of those core materials.
Let's turn our attention to the ultimate goal, then. What is the overall vision for 2040? What does success look like for RoadMap 3.0?
The vision is nothing less than complete domestic control across the entire industrial chain, from those specialty materials we just discussed all the way to the finished vehicle.
And there's a number attached to that, right?
There is. Quantitatively, the goal is reaching over 4 million FCVs in use. Strategically, the technology has to compete comprehensively with battery electric vehicles and internal combustion engines across all applicable scenarios.
Which means achieving parity or superiority in total cost of ownership, reliability, and performance.
In their designated segments, yes.
4 million FCVs is a massive undertaking. So how does the roadmap structure this industrial climb? It outlines 3 mandatory strategic milestones.
And this phased approach is critical for resource allocation and for managing technical risk. The 2030 milestone is the immediate focus. It's all about scale-up and capacity building.
With the target of at least 500,000 FCVs.
Right. This phase is about industrial validation, proving that the initial technical advances can be mass-produced efficiently.
Then we get to the 2035 milestone.
Here, the scale doubles to at least 1,000 FCVs, and the strategic focus shifts. It becomes a dual focus on both commercial and passenger markets. And critically, this phase mandates the deep application of AI across the value chain.
And this is the commercial turning point. The tech must achieve cost competitiveness with BEVs in most scenarios.
It is. If they fail here, the 2040 vision is just unattainable.
And that 2040 milestone is the realization of the full vision.
Full market competition, targeting at least 4 million FCVs. This demands large-scale, high-quality, ultra-low-cost production across the entire chain, establishing global leadership.
The emphasis on heavy commercial transport seems to be a global consensus. How does this roadmap align with, say, Japan's approach?
The alignment is strong. It reinforces that strategic pivot toward heavy logistics. Japan's overall FCV goal is smaller, 1.5 million by 2040, but their breakdown is highly instructive.
How so?
They plan for 80% of those 1.5 million FCVs to be heavy-duty vehicles. This shows that global players recognize the clear advantage of fuel cells in heavy transport, where battery weight really limits payload capacity.
This means the strategy is profoundly rational. Instead of immediately fighting a difficult cost battle against BEVs in the small vehicle segment.
Which is already saturated.
Right. They are using the high-power, high-utilization demands of heavy trucks to force the necessary durability and cost breakthroughs in the stack. And that technology, once it's hardened by the truck market, can then be cascaded down to make the passenger vehicle commercially viable.
It's the textbook definition of using a high-stress application segment to pull an entire foundational technology across the valley of death. The technical requirements needed to run a 49-ton truck for 1 million kilometers will automatically solve many of the durability issues plaguing passenger car stacks.
Okay, let's look at the numbers that underpin this strategy, starting at the vehicle level. We'll use the 49-ton heavy truck and the B-class passenger car as the benchmarks.
The targets for the 49-ton truck are ruthless. They have to be. They are meant to define the new standard for heavy logistics by eliminating diesel's primary advantage: longevity.
That longevity target is genuinely shocking. 2.0 million kilometers by 2040.
Yes. Truck life has to double from the 2030 target of 1.0 million kilometers by 2040. And to put that in perspective, that durability is necessary to achieve TCO competitiveness. It implies a fuel cell system designed for a minimal midlife overhaul.
Comparable to or even exceeding the most reliable long-haul diesel engine.
Exactly. That reliability mandate completely redefines the supply chain.
And what about the crucial cost mandate?
The purchase cost has to drop drastically, from less than or equal to 800,000 CNY in 2030 to under 500,000 in 2040.
Given that a smaller bus is still over a million today, getting a much larger truck down to 500,000 is a huge manufacturing challenge.
It's a transformation mandate, not just an R&D goal. And this has to be coupled with efficiency gains. Hydrogen consumption needs to drop from 8 kilograms per 100 kilometer down to 6.
These vehicles also need to operate everywhere. The environmental requirements are non-negotiable for logistics.
That's right. The extreme environment targets for 2040 show a focus on conquering all geographies. Operating temperature has to range from that of 45 degrees C to 60 degrees C, and altitude capability up to 4,000 meters.
Which targets use across high plateau and cold northern territories.
And achieving those extremes requires materials that can handle massive thermal cycling and air compression systems that can compensate for thin air without performance degradation.
Now let's look at the B-class passenger vehicle targets. Here the focus is more on consumer acceptance, affordability, and lifetime ownership.
The PV durability target is equally ambitious. It rises from 200,000 kilometers, or 8 years in 2030, to a phenomenal 600,000 kilometers, or 15 years by 2040.
That's triple the durability of a standard car. It transforms it from a consumer good into a nearly lifelong asset.
Or a perfect candidate for long-term ride-sharing fights.
But the single most challenging target here has to be the cost. Less than or equal to 120,000 CNY by 2040.
That target is the ultimate commercial pressure point. To deliver a sophisticated B-class FCV at that price, the cost of the fuel cell system, the stack, the MEA, every single component has to be reduced to near commodity pricing.
It can't be achieved through volume alone.
No. It requires every upstream cost goal to be hit simultaneously. This target represents the point where FCVs are no longer a niche technology, but a mass market alternative.
Okay, moving from the vehicle wrapper to the system layer. These system metrics are what directly drive those durability and cost figures.
And we're seeing a clear manufacturing mandate here. For commercial systems, power must peak at over 350 kilowatts by 2040. System life has to hit at least 40,000 hours, which aligns perfectly with that 2 million kilometer vehicle goal.
But the financial leap is staggering. The system cost must drop from 570 CNY per kilowatt in 2030 to just 270 CNY per kilowatt in 2040.
A 52% cost reduction in 10 years for a highly complex system.
What kind of manufacturing innovation is required for that kind of scale and cost compression?
This moves the challenge entirely out of the lab and onto the factory floor. It requires a transition to automated high-throughput, gigafactory-style manufacturing for fuel cell systems.
Standardizing components, optimizing supply chains.
And leveraging AI for quality control and predictive maintenance. If that 270 CNY per kilowatt target is missed, the 4 million vehicle vision fails. Simple as that.
And efficiency. Rated efficiency of over 60% by 2040 is crucial, since fuel cost is the dominant TCO factor.
It is non-negotiable. Every percentage point saved is hydrogen saved, directly lowering the fleet TCO. For passenger systems, the focus is slightly different, more on compactness and quick readiness.
So volume power density has to soar to over 1,000 watts per liter.
Right, to maximize interior space, and peak efficiency has to hit over 72%.
And the cold start capability reflects the importance of consumer experience.
Yes. Reducing the cold start time at -40°C from 90 seconds in 2030 to just 50 seconds in 2040 is a critical engineering challenge. It requires sophisticated, AI-driven thermal management and materials capable of rapid heating without degradation.
Which links right back to overcoming the current PEM and BOP limitations.
Exactly. And speaking of BOP, the supporting components have their own hyper-efficiency targets. The DC-DC converter needs to hit 98.5% efficiency. The thermal management system's highest coolant operating temperature must rise to over 120 degrees Celsius.
Which puts severe demands on every plastic, seal, and heat exchanger in the cooling loop.
Over a 40,000-hour lifespan, yes.
We've established that the entire RoadMap 3.0 hinges on fixing the core lag at the stack and material levels. Let's look at the specific stack targets required to unlock these vehicle and system metrics.
The commercial stack targets are the most demanding. Peak power needs to reach over 400 kilowatts by 2040. Life has to hit at least 45,000 hours, significantly surpassing that international 25,000-hour benchmark.
That 45,000-hour target feels almost insurmountable, given the current domestic ceiling is 16,500 hours. How do they justify such an enormous leap?
They justify it through the cost target. Because if they achieve the cost target, they must have solved the durability problem. The cost needs to drop to an ultra-low, less than or equal to 160 CNY per kilowatt in 2040.
So the two metrics are inextricably linked.
They are. The only way to hit that cost is to eliminate expensive materials like platinum and simultaneously ensure the stack never needs replacing prematurely. Hence the need for 45,000 hours of life.
For the passenger stack, the focus is pure density.
Yes. Volume power density has to surge to over 9.0 kilowatts per liter by 2040. And maximum working temperature also rises to over 120 degrees Celsius, reflecting the thermal stress that comes with that.
Let's revisit the bipolar plates. The cost targets require massive industrial scaling. What's the goal for high throughput production?
This is a classic example of technology being constrained by manufacturing engineering. To achieve that 2040 cost target of under 25 CNY per kilowatt, production speed for metal BPs has to become lightning fast.
And the target number is?
The film coating manufacturing speed needs to go from 1 second per piece in 2030 to an astonishing less than or equal to 0.3 seconds per piece by 2040.
Wait, 0.3 of a second to stamp, coat, and verify a plate? How is that even possible?
It requires continuous roll-to-roll manufacturing processes with nanometer-level precision. This isn't an R&D problem. It's a pure capital expenditure and automation mandate. Total automation, ultra-fast laser welding, advanced process control.
And now to the most ambitious target of the entire roadmap, the membrane electrode assembly and critical materials. The fate of the 4 million FCVs ultimately rests here, specifically on platinum reduction.
This is the centerpiece of the cost reduction strategy, and the goal is a deliberate effort to leapfrog international competitors. The 2040 target for cathode PT loading is set at an ultra-low, less than or equal to 0.12 milligrams per square centimeter.
That is extremely aggressive. How significant is that compared to the current global best?
It's profoundly significant. Current commercial leaders like Toyota operate around 0.17 grams of PT per kilowatt. This goal, if realized, would mean the material cost of the stack is largely decoupled from the volatile platinum market.
Giving the domestic industry a massive structural geopolitical cost advantage.
Exactly. And the corresponding MEA cost target of just 80 CNY per kilowatt by 2040 reflects the necessary success of this PT reduction.
What material science breakthroughs are explicitly mandated to enable this while also meeting the high temperature and durability targets?
The roadmap identifies the period between 2036 and 2040 for achieving full breakthroughs in new material systems. The high-temperature durability goal requires the max operating temp to reach over 130 degrees Celsius.
Which demands entirely new PEM resin chemistry.
It does. And there's a serious push to move beyond precious metals entirely by focusing on non-precious metal catalysts and the practical, large-scale application of alkaline anion exchange membranes, or AEMs.
So they are betting the house on fundamental material science breakthroughs that haven't been fully proven at scale yet, but which would solve the cost problem permanently.
It is a high-stakes, high-reward strategy. The ultimate cost and life targets are impossible under current materials constraints. Therefore, the strategy mandates a paradigm shift in materials discovery.
We've seen these enormous gaps between current performance, 16,500 hours, stack life, and future targets like 45,000 hours. Traditional trial and error R&D, it just can't close these gaps in time.
It can.
And this is where the Roadmap 3.0 introduces a profound strategic shift. The reliance on artificial intelligence and digitalization.
This is the how we get there section, and it's the most modern and ambitious part of the plan. Historically, testing a new catalyst or membrane meant months of synthesizing and testing.
Right.
AI is introduced as an accelerator and a quality control mechanism to solve the fundamental material consistency problems that define that core lag. The strategy is a phased integration, aiming to create a vertical large model across the entire chain.
Let's break down that phased integration. What does the 2030 early stage look like?
The initial phase is focused on data infrastructure. The industry starts building vast, clean data repositories and deploying foundational AI agents. These agents immediately begin optimizing early-stage design parameters, control algorithms for BOP components, and process optimization on manufacturing lines.
So it's about building the digital foundation that future models will be trained on.
Exactly. By the 2035 mid-stage milestone, the systems become much more sophisticated.
Moving towards specialized AI.
Yes, this is where specialized vertical large models are developed. These are AI systems trained specifically on the massive proprietary datasets of the stack, MEA, and system domains. And critically, AI begins assisting material informatics, or MI, for high-throughput material screening.
Allowing researchers to digitally simulate thousands of potential new PEM or catalyst combinations before running a single expensive lab test.
Right. And digital twin simulation platforms are rolled out to predict failure mechanisms instantly.
So let's connect that directly back to the core lag issues. How does a vertical large model solve the manufacturing consistency problems in PIMS and carbon paper that traditional R&D failed to address?
That is the ultimate test of the AI strategy. The challenge in PMs was that plus or minus 1 micron thickness variance. Traditional quality control relies on sampling. An AI-driven system can continuously monitor and correlate material inputs and process variables in real time.
Instantly adjusting feed rates or temperatures to guarantee the required consistency across the entire output.
It moves from reactive quality control to proactive continuous process optimization guided by a massive data set. The same applies to the carbon paper consistency issue. AI models can predict material performance from the manufacturing parameters, ensuring only highly consistent batches proceed.
And by the 2040 mature stage, AI permeates every aspect of the operation.
By 2040, the goal is total integration. Comprehensive vertical large models cover materials to vehicle segments. More importantly, they will implement a cloud edge and multi-level diagnostic and control system capable of monitoring and optimizing the performance of those 4 million FCVs in real time.
And what does that cloud edge end system allow in practical terms?
Truly intelligent fleet management. For instance, digital twin tech provides rapid prediction of stack failure based on real-time data from the end vehicle. If a truck drives up a mountain, the edge controller gets instructions from the cloud model, adjusting the BOP and thermal management in real time to prolong stack life.
So the integration of AI isn't just a technological add-on.
No, it's the mandated infrastructure that allows them to achieve those previously unimaginable durability and cost targets by eliminating inefficiency and inconsistency at every single level.
So this deep dive into the fuel cell technology roadmap 3.0 provides a powerful, highly structured view of the next 2 decades in clean energy.
It really does. We started by diagnosing the current state as application-led, core lag, great systems, but massive deficits in durability and core material cost.
We then explored the rigorous strategic response, a phased approach aiming for 4 million FCVs by 2040. This strategy dictates a strategic climb, forcing breakthroughs in the high-stress, heavy-duty truck segment to fundamentally solve the problems.
Right, solving durability and low-cost manufacturing, ultimately aiming to achieve cost parity with traditional power systems. The quantitative targets are just astonishing: 2 million kilometers of vehicle life, 45,000 hours of system life, and a cost reduction that mandates the system price drop below 300 CNY per kilowatt.
And crucially, the roadmap lays bare that the entire strategy relies on eliminating the need for expensive platinum by targeting that ultra-low loading of 0.12 milligrams per square centimeter.
And the most important takeaway for you, the learner, is recognizing that this plan requires more than just incremental engineering. The reliance on artificial intelligence and vertical large models is the explicit recognition that traditional R&D methods are insufficient.
AI is the engine designed to accelerate material science and manufacturing precision to a degree never before attempted in this sector.
The blueprint is comprehensive, and the stakes are enormous.
So if the success of this 4 million vehicle hydrogen future rests entirely on realizing these ambitious targets, we are left with a fundamental strategic question that will define the winners and losers of the hydrogen economy. On the one hand, we have the material science challenge achieving that ultra-low platinum loading, which requires fundamental, unproven chemical breakthroughs.
And on the other hand, we have the advanced manufacturing efficiency challenge, achieving that lightning-fast, high-precision bipolar plate production at less than 0.3 seconds per piece.
Which of these two hurdles, the pure material science quantum leap or the high-speed industrial automation mandate, will prove to be the most difficult to clear by 2040 and thereby determine whether this strategic roadmap succeeds or fails? That is the billion-dollar question you now have the tools to analyze.